Alright, for today, we want to look at something I introduced as a concept on Friday, and that was the indeterminate form. The indeterminate form is a case where when you try to plug in what x is approaching in a limit, you end up with 0 over 0. Okay? Now, there's a couple of things to recognize here. First of all, this isn't 0 over something, because 0 over something equals 0. Right? 0 over 5 is 0. In that case, you don't have an indeterminate form. The limit would equal 0. Also, though, it's not something over 0. It's not 5 over 0 or 10 over 0. That's undefined, but that's going to be different than the case here. I want you to think back to Unit 3 when we were looking at rational functions. You determined the domain. You know, you factored the domain like x plus 3 and x minus 2. And then you said the domain is x cannot be negative 3 or 2. And in those cases, those values gave you one of two things. What did they give you?
A whole or an asymptote.
There we go, a whole or an asymptote. That distinction is going to be important here, okay? And the reason why, it's actually easy to distinguish between them. If you got, say, 5 over 0, that's not what we're talking about. That is going to be a point on the original, or a spot on the original function where we have a vertical asymptote. Okay? That's not an indeterminate form. That actually is going to be a case where the limit does not exist. Okay? We're looking at the case where you get 0 over 0, and that's a time where you get a whole. Okay? So, the same procedure that we used to find wholes back in Unit 3 is one of the methods, and really the basis of the other method too, that we're going to use to find the limit of an indeterminate form. Okay? So we have two techniques. One is the dividing out technique, the other is the rationalizing technique. Both of these, I have one example already worked out that we're just going to look at, and then we're going to have an example or two that we actually try. Okay? So let's pick up first with the dividing out technique. Here you see all the work, but let's hone in on the problem first of all. We're trying to find the limit as x approaches 1 of x minus 1 times x cubed minus x squared plus x minus 1. And approaching this problem, you see a line on the top, a cubic on the bottom. The first natural attempt would be to simply plug in 1 and see what happens. Okay? Unfortunately, though, in this case, when we plug in 1 to the numerator and denominator, they both end up equaling 0. So we get the indeterminate form. And that means we've got some more work to do. Okay? Now, how did we identify wholes back when we were doing rational functions?
So we can cross out, like factor the.
Okay, you would factor it out, and if it was a whole, you would be able to cancel out the factor in the denominator that gave you that element that wasn't in your domain, right? So, in this case, we're going to do actually the same thing. Notice here, we're going to factor the denominator. By the way, this is going to be a good lesson or two here that will help us practice our factoring again, okay? So, we're factoring this by grouping the first two terms and the last two terms. In the first two terms, they have a common factor of x squared, leaving us with x squared minus, x minus 1 in the parentheses. This second group here already matches what was in the first set of parentheses, so we can just see this as a plus 1 times x minus 1. And factoring by grouping here, we pull out the common factor of x minus 1 here. Alright, we pull that out. And what's left then is the x squared and the plus 1. That goes in the other set of parentheses. Okay? So again, a quick review of our factoring by grouping. So how do we use this? Well, let's go back over here to the limit. Once we see how to factor our denominator, we can rewrite the limit as the limit as x approaches 1 of x minus 1 over x minus 1 times x squared plus 1. And notice here what happens. If we look at this as a whole unit, it matches the factor here on the bottom, and those cancel out, leaving us with the limit as x approaches 1 of 1 over x squared plus 1. Okay? So notice here the denominator, if I plug in 1, the denominator is not going to be 0. The numerator equals 1. It's never going to equal 0. So now I can do direct substitution, and I get a half. Okay? So the limit equals 1/2. Now, as you can see over here, well, because we got 0 divided by 0, which is undefined. Okay? That's the whole point of this thing. We're getting that indeterminate form, 0 over 0. Notice this is the graph that we have here. And the point 1 1/2 is the whole. Okay? So notice the relationship of what we're doing now to what we did before. Before, that 1 was not in the domain, so we reduced it and then we plugged in the 1 to figure out the y coordinate of the whole. Here, what we're approaching, what x is approaching, is the x coordinate of the whole. And what the limit equals is what we used to recognize as the y coordinate of the whole. So guys, you're doing the same work. It's just in a new context, and you're interpreting your result just a little bit different. Okay? Does that make sense? Okay? Why do we have two limits?
Yeah, because y is half and y is the other.
1 is not the limit. 1 is what x is approaching.
Yes.
So, notice here, as x gets closer to 1 here from the left, and as x gets closer to 1 from the right, the y value on both sides is getting closer and closer to 1/2. So that's why our limit equals 1/2. So this is the answer right here, 1/2.
But it can never reach to 1/2.
You're right, it can't. And that's why sometimes limits are a little hard for people to grasp and accept in their heads, because the limit, the function does not have to equal that value. Remember, our definition of a limit is the value that the function is approaching. That's the key there. We are approaching 1/2, even though we never actually equal 1/2, it's approaching 1/2. Okay?
But it's like it's approaching to a certain number, so that is still.
Yes.
Okay.
Yes, that's correct. It's approaching a specific number, so that's our limit. Okay? Let's try an example or two of these. Okay? Here's a relatively simple one to factor. Take a sec here and try this one on your own. All right, someone tell me what they did here.
Factor it out, x minus 2, x plus 6.
Okay? So x minus 2, x plus 6 on the top.
Cancel out the x minus 2 and then cancel.
Okay, so we're taking the limit as x approaches 2. By the way, I didn't hear anyone sound confused or anything, but a lot of times the computer won't put the x approaching 2 underneath the limit. So if you see it kind of to the side like that, that's just a limit of using the computer. Alright. Alright, so like you guys said, it cancels out there. Whoop. It cancels out there. And we're now taking the limit as x approaches 2 of x plus 6. So guys, is x plus 6 continuous around 2?
Yes.
What is x plus 6?
8.
Well, no. What is it? It's a linear. It's a line. All right. What's the domain of a line? All real numbers. Yeah. Okay. So, is it continuous around 2? Yes. So we can plug that in, and we get the limit equal to 8.
So what was the point of that? Making sure it was linear, or
I just want you to think. I don't want you to just like
plug it in?
randomly plug stuff in. I want you to think. In order to be able to plug it in, you have to have something that's continuous around the value you're approaching.
When is it not continuous?
If we still had, like, maybe the denominator was x minus 2 quantities squared. So only 1 canceled out, and then we have an x plus 6 over x minus 2. Then you'd have 8 over 0, which that limit wouldn't exist. Okay? So there'd be a difference there. So think as you're doing it. Here's another one using some trig. Let's see how good a memory we have. What is sine of 2x?
2 times sine x.
Why?
And sine x times
Sine
cosine.
negative sine.
Two.
There we go. Put them together. Sine of 2x is 2 times sine of x cosine of x. Alright, so we're taking the limit as x approaches 0 of negative 2 sine x plus 4 times 2 sine x times cosine x all over sine of x. Alright? So there's your identity for sine of 2x, your double angle formula. Alright? So take a second and go from there. Alright, what are you doing to try to cancel stuff out?
Get rid of the cosine. Get rid of the constants outside, like decreasing them.
You could, that's not going to help us reduce stuff out.
Well, you want to get to sine x on the top. So
We want to get a sine of x on the top that we can cancel out, right?
you can keep the cosine x, but you just want to get. So would you factor out a negative 2?
You can. All that it really matters that you factor out is the sine. If you factor out a sine of x on the top, you have negative 2. We'll put the 4 and 2 together now to get 8 cosine x. So negative 2 plus 8 cosine x times the sine of x over sine of x. Now, you can cancel the signs. Alright? Now, is negative 2 plus 8 cosine of x continuous around the x equals 0?
Cosine's always continuous.
Cosine's always continuous, yeah. And the negative 2 just shifts it up 2 units, and 8 just stretches it, so it's still going to be continuous. Alright, so we can just plug in 0. And you get negative 2 plus cosine 8 times cosine of 0. What's cosine of 0?
Pi over 2.
1.
No, it's 1, okay? Good, I heard somebody saying it. It's 1, so negative 2 plus 8 times 1 is 6. So the limit equals 6. Yes.
Why can't we just cancel the sine x from the beginning?
right here.
Yeah, yeah.
We can't cancel it at that point because,
I mean the,
oh, on here? If you see it, you could cancel it out from all three parts, like both of those and that one.
yeah, but how would they get that?
Okay, so that's one method. Let's look at our other method. Again, our second method is going to take something that we've done in the past and just apply it to a brand new context. Okay? And that is the rationalizing technique. This one seems a little bit more complex, but it's really not too bad. Okay? So let's look initially at the problem we've got here. We want the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. If we try to plug in 0, we end up with 0 over 0. So again, we need a different strategy than just evaluating in order to get our limit here. Okay? So, earlier in the year, when we had a radical in the denominator, we would multiply by a form of 1 to rationalize in order to get that radical out of the denominator. Now, however, we really don't care where the radical is. If we're getting something that is giving us 0 over 0 and it involves a radical, we're going to multiply by a form of 1 to try to get the radical out of that part of the fraction and into the other part. Okay? Now, in this case here, we have a radical minus 1. So what we're going to do is we're going to multiply by the conjugate of that. Alright, we're multiplying by the conjugate. So while it was the square root of x plus 1 minus 1, now we're going to do the square root of x plus 1 plus 1. Notice here, the conjugate, we want to multiply by the radical plus 1, because now when we multiply, if you were to FOIL these together, the outers and the inners will be opposite, so they will cancel out. So we just have the first, so radical x plus 1 times radical x plus 1 is just x plus 1, and we have the last, negative 1 times 1 is minus 1. Okay? Now the whole point of doing that is so that once we simplify the numerator, x plus 1 minus 1, those cancel and that's just x. And notice in the denominator we've got an x as well, so those can reduce out. The x's reduce out. And now, yes, we have something with a radical on the denominator, but we have something that when you plug in 0, you don't get 0 over 0 anymore. Okay? Now I know this right here says x cannot equal 0. That's the domain originally. Notice now, this function x is allowed to equal 0. So we can plug in 0, and now that we have this simplified, we can rewrite the original problem as the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And then we can evaluate that limit by simply plugging in 0 for x. We do that and we get 1/2. So the limit equals 1/2.
Why do you have to rewrite the first equation again?
Again, because if you just plugged in 0, you'd get 0 over 0.
No. Like, you already have the new one. Why can't you just, like, plug it in on the top? You said that you had to rewrite it again. You couldn't do direct substitution when you have one over roots.
Well, we're plugging this in. We're just showing the original problem again. The original problem's right here. We're replacing that original function with the equivalent function that's been reduced or rationalized. And the rationalized form, we're able to actually plug 0 in to find the limit. Okay? Now, real quick, notice here, this is what this function would look like. And there's the hole. X is approaching 0 from both sides. Okay, X is approaching 0. The Y coordinate is approaching 1/2. So the limit, it equals 1/2. Okay? So let's try one of these. Okay? In this case, the radical is in the denominator. Alright? What form of 1 are we going to multiply by here?
Square root of x plus 5.
Yeah, square root of x plus 5. Notice if I plugged in 25, 25 minus 25 is 0. The square root of 25 is 5. So if I subtract 5, I get 0. So this is the indeterminate form. So I am going to multiply by root 5, root x plus 5 and root x plus 5. Okay? So our numerator is x minus 25 times root x plus 5. What does the denominator equal?
X minus 5.
No?
X minus 25.
That's right. Yeah.
X minus 25. Which now we can cancel out. And that canceled out the whole. So now our end result, we're taking the limit as x approaches 25 of the function that doesn't have the hole in it anymore. That is continuous around 25. Okay? That's just the function.
10.
It's shifted up 5 and it goes like this. Okay? When x is 25, we have the square root of 5 plus 5. Square root of 25 plus 5. So that's going to give us 10. Alright?
I have a question in this one. I'm not sure if it would work for everything. But
Yes.
so x minus 25 could also be seen as the square root of x plus 5 times the square root of x minus 5, right?
Yes.
Okay, and then if you were to solve for that, right, the only solution would be where x equals 25, right? Because that would equal 0. If
Okay.
you're equaling, and since the other one doesn't have a solution, then you could plug the solution, which we already knew, obviously, because it's x is approaching 25, into the unsolvable one, square root of x plus 5, and then it would be 5 plus 5, and we would just have our answer there.
Okay. Yeah, basically what Grant's saying here is another way that you can see ones that are like this is, you remember factoring difference of squares?
Yeah.
Like you did x squared minus 9. You took the square root of x squared and got x of x, and x, and then you did the square root of 9 and you had a plus 3 and a minus 3, and there's your conjugates. That works even if the two terms aren't perfect squares. So for example, here we have x minus 25. I can do plus 5 and minus 5 as long as I do the square root of the first term and I make it root x and root x.
Then you have to check for holes, don't you?
In that case, notice if I factored the numerator into that and then it was over the radical x minus 5, notice that would cancel and I'd be left with the root x plus 5 again. Okay? So if you see the difference of squares, the old algebra has to be two perfect squares really wasn't all true. you actually can do the difference of any squares. If you just take the square root, you can even do the difference when it's not a difference.
I know.
If you make it minus a negative, but then you end up with complex numbers, which we aren't in our limits, okay? Alrighty guys, have a great day.